Hello everyone and welcome. In this video I'm going to talk to you about wheels and the aerodynamics of wheels. Now, next to a rider, the second biggest impact on drag on a bike are the wheels, and I'll come on to why in a moment. In this video I'll tell you what the difference is between this sort of wheel, a very shallow wheel, a deep section aero wheel, and also some of the aerodynamics terminology and intricacies involved in this. As part of the explanation process, I will have simplified things. So if you are an aerospace engineer out there, I apologise in advance, but trying to condense an entire topic into a short video is not exactly easy. So a word on terminology, because this is quite important for this video because it's quite technical. This is the top of the wheel and tyre. I'm going to refer to the tyre and wheel almost in unison, but this is the top. This is the front, so this will be hitting the air first. This is the back of the wheel tyre, and the bottom is the bit that's in contact with the ground. The other thing that I need to mention is when I refer to leading edge and trailing edge. Leading edge is what hits the air first, and trailing edge is where the air leaves last. So this will be the leading edge on the front of the wheel. This will be the the trailing edge on the front of the wheel. At the back of the wheel, this is the leading edge, i.e. the carbon, and the trailing edge is the tyre. Now, what we're interested in bicycle wheel aerodynamics is the force drag. Now, drag is something that is designed to slow the bicycle down. Drag is a function of a number of things. The first one is the density of the fluid that it's going through. So a fluid to an engineer can be air, can be water, can be some gas like acetone or nitrogen or whatever. It's just a fluid. Okay, the fact that it is a gas is irrespective of the fluid, it has properties. The next one is the velocity that the object is travelling at. So if you have no velocity, you cannot have any drag. If you are going at, for argument's sake, 10 kilometers per hour, you experience a drag force. If you go at 20 kilometers per hour and you keep the same object, roughly speaking, the drag force that you will experience, it will be 4 times more, because the drag force is proportional to the speed squared. The final one, and I guess the one that we're really interested in, is a combination of the size of an object, so the cross-sectional surface area of the object, and what the object's shape is like. And that determines, on a bicycle wheel, quite to a large extent, how much drag that you will experience. Now, coming back to density, density is quite important because it's not very equal across the planet. And the reason I say that is in density terms, you can have a variation between sort of 1.05 kilograms per cubic meter and possibly even 1.3 kilograms per cubic meter. So that's the mass of 1 cubic meter of air, i.e. 1.3, 1.2 kilograms. If you were to take a rider in, for example, Australia, who was travelling along at, for argument's sake, let's say 30 kilometers per hour and putting out 300 watts, and then brought him back to the sunny climes of the UK in winter and asked him to do the same 300 watts, he wouldn't be able to do 30 kilometers per hour. Typically, he would need an extra 20%, i.e. another 60 watts, to be able to go at the same speed. So that's how much of an effect density can have. At the same time, that's really a function of temperature. So in Australia, I don't know, maybe 30 degrees. Over here in the UK, 2 degrees, and that differential has the effect of increasing the power required. At the same time, the humidity of the air that you are going through also has an effect, because humidity has an effect on density. The more humid air is, the air is actually less dense. That might seem counterintuitive, but if you go on the internet and have a look for Avogadro's number, that will explain what that principle is. So I need to introduce the concept of relative speed in here, and the difference between speed and velocity. Now, I tend to use the two terms interchangeably, but there is a difference. Speed is a quantity that only has magnitude, so it is just a number, 35 meters per second or 35 miles per hour, 35 kilometers per hour. That is it. It is called a scalar quantity because it just has magnitude. Velocity is a value that has both magnitude and direction. For aerodynamic principles, we need to concentrate on velocity. So velocity for this bicycle wheel can be expressed in a number of ways. Usually you would just give it a direction with a minus or a plus. So if I define going that way as positive, then the top of this wheel is going in the correct direction. However, if I define positive as that way, this wheel is going in the opposing direction and is therefore negative. The signs are reversed at the bottom of the wheel because the wheel rotation means that at the bottom the wheel is actually travelling backwards, whereas at the top the wheel is travelling forwards. You might think, why is this important? Well, if this bike's on rollers and we're doing 30 kilometers per hour, the whole wheel is spinning at 30 kilometers per hour. The top of the wheel is going 30 k's that way, the bottom is going 30 k's that way. When you take the rider out, take him away from the rollers, put him actually out on the road, what happens is another effect happens. You've got air that's now hitting the bike. When the air is hitting the bike, if the bike is stationary and the tyre is not moving, air is hitting it completely at 30 kilometers per hour. However, when there is now rotation, i.e. the wheel is rotating, the 30 kilometers per hour, which is this hand, is now hitting the tyre that's also rotating at 30 kilometers per hour. You have a relative velocity there, or relative speed of 60 kilometers per hour. At the same time, at the bottom of the wheel, you have a relative velocity of 0 because the wheel is going that way at 30 kilometers per hour and air is also coming in at 30 kilometers per hour. So by definition, there is 0 velocity and therefore no drag. So to summarize that sort of section, basically the top of the wheel, top half of the wheel, is going in a direction that is unfavorable from a drag perspective. The bottom half of the wheel is going in a direction that is favorable from a drag perspective because it's in the direction of the wind that's hitting the bike. Now, on a bike, there are really only two ways to generate drag. One is called skin friction drag, and the other is called pressure drag. Skin friction drag is the friction that the air has to overcome to just go around you, basically. So if I put my hand like that, I've got a frictional force, frictional area that's just caused by the air going over it. It actually makes my hand hot as air goes over it. Pressure drag is a bit more complicated. Pressure drag is actually caused by a differential in pressure, and that can be caused by a differential in speed. So with this sheet of paper, we're going to demonstrate what pressure drag actually feels like. So I'm going to blow over the top of the piece of paper. You saw the paper rise, and the reason why the paper went up instead of, most people probably think it comes down, is I'm blowing over the top of the paper. By me blowing over the top of the paper, I've actually reduced the pressure on the top surface of the paper. Because there's a drop in pressure relative to the bottom of the paper, which is still seeing high pressure, it lifted the paper up. On a bike, same thing happens. You've got areas of high pressure and low pressure. When the two interact, they generate something called vortices. Now in nature, you see this all the time. High pressure, low pressure, that actually causes wind. If it's in a very localized scenario, a vortex is a tornado, a cyclone, or a hurricane. They are all forms of pressure differential. So in the middle of a hurricane, you've actually got no movement of air because the pressure is fixed. There's no differential, and people often hear, talk about their eardrums popping, and that's because as a hurricane or a tornado is going overhead, the air pressure is changing, and it's the same thing on a bike, albeit at a lot less ferocious velocity. We're going to get to the juicy bit, which is to explain why this wheel, this Zipp wheel, is more aerodynamic than that Shimano wheel there. And the reason is not probably what you would think. The first thing to consider is let's consider the path of the air that comes over the centre of the wheel. So air comes over here. First thing here is this little area where the clincher clinches into the rim bead. That is going to generate a bit of turbulence. Then we go across here. Now Zipp claim that this is to reduce drag. I can categorically tell you that's marketing bollocks, because the flow over here is not going to be in a Reynolds number, which is another complicated term, where that would make a difference. So I think that's just marketing rubbish. So we go over here, detach from this place, and then carry on going past the hub and then over towards the back of the wheel. The actual aerodynamic advantage in a deep section wheel is nothing to do with this sexy toroidal shape. That has very, very little effect. It will have a small amount, but not very much. A bigger advantage comes from pure geometry, and that is because of what we'd call aerodynamically is the chord length of the aerofoil. So if that is an aerofoil section, we would determine that as the chord length. So horizontally, that chord length to the edge of the tyre is about, on this wheel, 10 centimetres. However, as we move down the wheel, this chord length gets longer. So that's 14 centimetres there. At probably the maximum, it's 40 centimetres. So you've got an area where you get detachment. If you minimise that area of detachment, which you do by increasing the depth of the wheel, you will make the wheel more aerodynamic, which is why a disc wheel is fundamentally more aerodynamic than any of this type of wheel. So I'll repeat the process on the Shimano wheel. Now on the Shimano wheel, the flow is actually coming from that direction, that way, but the cross-sectional area there is around about 6 centimetres. So that's my chord length there. At its longest point, which is around about there, it's 30 centimetres. So we've instantly lost 10 centimetres, but it's 10 centimetres multiplied by the height as well. So 6 times 30 is roughly 180 versus 11 times 400, which is 440. And that kind of rough guesstimation is how you determine the aerodynamics of the wheel. That has far more effect than the section. This is very, very akin to a box section wheel. So there's hardly any tapering or anything like that on this wheel. One of the subjects that a lot of marketing is based on is something called yaw angle. Yaw angle is the relative direction that the bike is travelling in relation to the direction the wind is coming out. So if we were to go square on, the yaw angle will be 0. If we were to tip the bike slightly so that the air is coming that way and my bike's pointing kind of like that way, what happens is the air starts to detach from the bicycle wheel rim. The more yaw angle you have, the more detachment you're likely to get. At a certain angle of yaw, it is aerodynamically inefficient to have a deep section wheel, and that is dependent on the geometry of the profile of the bike wheel. At the same time, the other thing that you experience is if there's a lot of yaw angle, is the bike will become unstable and effectively a crosswind will try and tip the bike over. One of the other hot topics that is the flavour of the month at the moment is fitting wide tyres to wide rims. Now, the actual drag is caused by this dimple here and the bulge in the tyre when you get round to the back of the wheel. Basically, the basic guidance is if you're going to fit a wide tyre, make sure your rim is wide. Don't fit a wide tyre to a narrow rim because it'll balloon, and the ballooning will cause drag on the far side. So you rejoin me in what I can best describe as the engineering mecca that is my computer room. And unfortunately I don't have a wind tunnel, so what we're going to do is go through this on Solidworks with some CFD, and that will illustrate some of the flow patterns a bit better. So what we have here is a wheel that I've drawn. Obviously there's some assumptions in here because there's no hub and there's no spokes. I apologise for the fan noise that you can hear, but running Solidworks is not exactly a non-processor intensive process. So this section is typical of what a Shimano section would look like. So let me show you. I've taken a section through the wheel. So this is the tyre. This is that typical bulge that you would get if you fitted a tyre to a slightly narrow rim. This is the brake track. This is the tapering section, and just a bit of rounding there just to make it look a bit better. That's typical of a Shimano wheel, probably a C50, although this rim depth is actually 80mm. Let me turn that off. Once you have that wheel, you can, on CFD, run an analysis where you can put flow through the wheel, add some rotation, and see what the airflow does. And that's what I've done. Now, I have prepared this earlier because it takes an absolute age to run it. So for a wheel of this complexity, it takes about 3 hours to run. If you've got a faster computer, it will probably go a bit faster than that. So what we have is these lines. Now these lines probably look like they're something from a weather map, but in reality what they are streamlines showing vorticity, and vorticity is effectively where the drag comes from. Now earlier I mentioned that drag comes from pressure drag and skin friction drag. The skin friction drag is small in comparison to the pressure drag. So pressure drag caused by a difference in velocity causes these things, which are vortices. And you can see one vortex there, another vortex there, another vortex there. Now the useful thing with Solidworks is you can actually see where the vortices are at any point in the wheel. So if we start at the bottom, the prophecy that I predicted was there would be very little drag. There is actually a small amount of drag, and that's because the velocity is not quite the same as the impact or free stream velocity, but you can see there's very good distribution of streamlines from the leading edge of the wheel tyre combination to the trailing edge of the tyre combination. This blue that you can see around it, that is where the cut through the wheel and tyre is. So I'm going to move this up, and you can see that, you know, in this area where we have no sort of free space and there is just one continuous section, there is very little drag. Okay, as we get towards the cut point, and when I say the cut point, that is where there's a gap between the leading edge of the the trailing edge of the front of the wheel and the leading edge of the back of the wheel. Down here there's nothing, but as we go up there's a definite point, and I've just screwed that up a bit, but here we go. There. So now we have clear air between the leading edge and trailing edge of the front and back wheels. Where we have that, you can see almost instantaneously there's flow disturbance, and this is detachment. So when air comes along, it comes along, keeps going, and then all of a sudden it detaches. When it detaches, all of this mess happens. So there's a vortex there, another vortex there, and then it hits the leading edge of the back of the wheel. If we carry on going a bit higher, this vortex business becomes more apparent. So you can see another vortex there, there's the start of one there, another one there, two, one here and one here, that are either side of this area where the tyre comes over and then meets at the bead. And also we've set up a slight bow wave, so we're compressing the air slightly in front of the tyre. Carry on going a bit higher, and I think that is the middle, oh, just slightly above, go a bit lower. That is the centre line of the wheel and tyre combination, and all of a sudden this is a stagnation point, and it's very, very clear to see you know, the vortex streamline position there is, that's just a stagnation point. We've got vortex shedding here, vortex shedding here, vortex is just immediately off the trailing edge of the front of the wheel. That flow is disturbed, it carries on going towards the back of the wheel,
and then we have some more flow disturbance. It's sort of a neatish shape, but it's an inverted aerofoil that's touching at the back of the wheel, and so it's not preferential. If we go higher, this vortex is still immediately apparent. Keep going, keep going, keep going, keep going. So this is what I would probably call a nasty section of airflow, for want of a better word. This top section. So there's some point to do with the geometry of the wheel and the fluid conditions that have applied that cause this massive vortex. Not quite sure what it is because I haven't really studied it in a lot of depth. But if we carry on going higher and higher and higher, so we're back now at the point where we have continual, a boundary that's continual from the front of the tyre to the back. There is no breakage in the wheel, and the flow is better than where there's a break in the wheel. If we carry on going higher and higher and higher, this is this nasty vortex here, and also flow disturbance off the top of the wheel. Carry on, keep going, keep going. So, just as we skim the top of the tyre, there's actually a lot of wake there. Vortex shedding there, vortex shedding there. This what I have is what's known as a computational domain. So I've just trimmed the section in this blue rectangle here. If I was to make it wider, you would see another vortex there, but that increases the computational time, so I haven't done it. So from this, what you can garner is, a number of things. The main thing to garner is on the bottom section of the wheel, the sort of airflow conditions are favourable because the wheel is rotating in the same direction of travel. So the vortex shedding, vortex development is nowhere near as bad. So look, if you look here, as we come back down the wheel, as we get near the bottom, there's hardly any vortices because the wheel spinning is in the direction of travel. Okay, when we get about a quarter of the way up, we're starting to get vortex development, but in here, look at that. There's just vortices everywhere. So that's why the top of the wheel has a lot more drag. Now, one of the things that I have done is I've tried to make a wheel that has a very, very sexy aerodynamic profile, and that profile is what's known as a NACA profile. So a NACA profile, if I bring this up, is the National Advisory Committee for Aeronautics. It's basically the precursor to what is now NASA. In here, the aerofoils are well studied, so you've got lift coefficient to drag coefficient, CDA, CL, all that kind of stuff. If you've got time and you understand that and you understand what Reynolds number and all that kind of stuff means, then by all means look at it. But what I've done is I've taken this aerofoil profile and made my own wheel. So let's show you that. So this is a NACA wheel. So if I take a section through the NACA wheel, you can see that it's a beautiful aerofoil profile. Now, commercially, Look, the brand, the bicycle frame brand and pedal brand Look, use this profile in some of their bike frames, 0024. If you're interested, the 00 means it's a symmetrical aerofoil, and the 2 and the 4 determine how thick it is and the point at which the maximum thickness is. You look it up on Wikipedia, it's very well documented. Anyway, this is a NACA profile. It's effectively modelling a 45mm deep wheel. Mavic tend to use this on their wheel rims, so this is almost a modelling of a Mavic wheel. I've done the same thing on this one. So let's start at the bottom. The flow characteristics on this wheel are a bit different. Now, what happens on the bottom of this wheel is, yes, we have a small amount of what's known as compression vortex generation. I wouldn't really get too fret up on that because it's well, it's hardly anything. And also this wake turbulence behind it, again, it's very, very uniform, and it's probably a limitation of the geometry and the CFD that I've used. I've made a lot of assumptions here to try and give you a model that will work, as opposed to spending ages and doing all the simulation that would take a week. So I've taken the hub out, taken the spokes out, and I haven't got some other little features in there. Let me just hit save. Right, then what we can do is we can do the same thing. So we can move this up. Oh dear. So we're going up, and we've still got this micro vortex generation here. And again, we haven't dissected the wheel at any point. We are still attached. We've got all of this happening over here, but there's no vortices, remember. There's disturbance in flow, but no vortices. And that's what we want to have. If we keep on going, again, still no vortices, although we're on the point of having vortices. So we've got flow separation. Flow separation here, we have to have flow separation because there's no material between these 2 points. And we've got some turbulence that's being generated at the front of the wheel. Note this wheel doesn't have that sort of pinch point where the tyre meets the rim. Carry on going. Now we have got some vortex generation. So we've got vortex generation here, 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 and here. The reason we have this vortex generation is because this aerofoil is basically into the wind backwards. So air's coming from the right hand side. We've got some small vortex generation, but from the trailing edge of this aerofoil, you can see there's no vortex generation. There is flow separation, but there's no vortex generation. If we carry on going a bit higher, this vortex here and here become more apparent, and that's because, again, this aerofoil is facing the wrong way. Now, around here, we have the start of vortex generation, so that is going to cause drag. But if you look, it's very, very long and slender, and it's also in the direction the wheel travels in. It's not going out at 90 degrees, so that's much more controlled. We're carrying on going higher and higher. Again, now I'm just looking to see if there's anything worth talking about. Now, okay, so now we're approaching the centre section of the wheel. We're almost bang in line, and we've got a fairly strong vortex there, but again, you can see it's in line, and that's what you want. You don't want it to be going off at 90 degrees. Keep going higher and higher. Okay, now we're in the unfavourable section of the wheel, because the wheel is now rotating in the oncoming direction of the wind. And okay, we haven't got much vortex generation there, but over here we're now starting to see vortex generation that's off to the side of the wheel. So things can only get worse from here, and sure enough they do. So we've got massive vortex generation here and here and here and here, everywhere. Also some more turbulent factors happening at the front. Keep going. There's a bit there. You zoom out. And we're going higher and higher and higher. So in this region, the aerofoil profile is very, very much longer than it was originally anticipated. And you can see the vortexes have diminished somewhat. Obviously off the trailing edge we still have that. And then we are back into the region where we have no free space between the front and the back of the wheel, so it's just as one unit. Keep going, and we are at this point here. At this point here, what we have is a skim off the top of the tyre. You can see this massive vortex generation over here. So that's where you basically your bicycle frame would be about here. So the forks would be about here, and that would be hitting it. And that's almost what you would call a Helmholtz vortex. So that concludes this kind of CFD bit of the video.
So to summarise in this video, you've learned quite a lot. First thing to consider is some of the aerodynamics around the tyre and wheel combination, and that is the top of the tyre and wheel generate the vast majority of the drag, and certainly the top half of the wheel tyre generate the vast majority of the total drag. The bottom of the tyre generates very little drag because the relative velocity is very small. The tyre width is very important, and especially this little groove in here. If you can take the groove out, that is a measurable advantage. Now the UCI actually banned Mavic from putting strips in there to improve the airflow, but if you're just on an evening time trial and you put some silicone or something like that in there just to bridge the gap, I don't think the marshals will say very much. The rim depth has far more effect on aerodynamics than any sexy toroidal shape or aerodynamic profiles. If you are going to go for an aerodynamic profile, I recommend a NACA profile, an NACA profile, especially Mavic wheels tend to use that. This kind of dimpled surface that Zipp put on their wheels, it increases the skin friction coefficient, but it's designed to reduce the pressure drag. Do I think it works? No chance, absolute rubbish. I think it's marketing crap, so I wouldn't go with that. I really hope you enjoyed this video. I imagine there's some questions to ask below. If you want to ask a question, use the comment box below. I'll do my best to answer them. Thank you very much for watching, and until next time.